Hi, this is Shoikat Majumdar. Today we will discuss in Basic Science and Humanities course Physics 1. The course code is BSHUPH101 and we will discuss the topic Polarization of Light in Module 2. Name of the module is Optics. Learning objective. Realize the importance of transverse nature of light, and light can be polarized by reflection and scattering. These are some pictures. Picture of the clear day, very hazy day, and moderate day. The blue color of the sky, or why did the mountains turn bluish? Because atmosphere perfectly scatters blue light. All these are polarization due to scattering. This is a well-known feature, polarization photography. The left picture that was taken, the glary sky. After using the polarizer, it reduces the sun glare, reduce reflections. The sky here darkens, increase the color saturation of the leaves as well as the sky, and reduces the haze. Maxwell in 1865 proposed the electromagnetic nature of light. He proposed that light is an electromagnetic wave. It has both electric field and magnetic field vibrations. These electric field and magnetic fields are perpendicular to each other and also perpendicular to the direction of propagation. In our figure, if we consider the blue arrows as electric fields and yellow arrows as magnetic field, so these two are perpendicular and also perpendicular to the direction of propagation as denoted by the white arrow. So these are the planes of electric field and magnetic field. Electric field vibrations are responsible for vision. Vibration of light means electric field vibration. This is only one plane we have extracted, that is the electric field vibration plane. Now in front view it becomes like this. Its plane of oscillation is along this direction. The arrow representing is the plane of oscillation. Now it is electric field, the light has many sided vibrations. So many vibrations is oriented like this, along this way or this way or this way. So this is the front view of this different vibrations. Now these are the atoms. Electromagnetic fields are produced by excited atoms. Suppose the vibration of this atom along this direction, this one is along this direction, this is along this direction. So many atoms having many vibrations in different directions. So common light source emit light that have electric field vibrations in all directions. So like incandescent bulb, candle, fluorescent bulb, etc. It has vibrations in all directions. Light having vibrations in more than one plane is called unpolarized light. Light waves having vibrations confined to only one plane is known as polarized light. That means light has many-sided vibrations. If we can convert the many-sided vibrations to a single-sided vibration, is known as polarization of light. Electric field vectors in an unpolarized light can be resolved into vertical and horizontal components. This is a simpler way of representing unpolarized light. Vibrations in different planes, and this is the front view of wave. Here is another view, that is side view of the wave. The double-ended arrow represents vibrations in the plane of the paper, and dot represents the vibrations are perpendicular to the plane of the paper. This is the dot perpendicular to the plane of the paper, and this is the double-ended arrow. This is the vibrations in the plane of the paper. Here the figure calcite crystal of crystallographic AA dashed. This is the calcite crystal. Its crystallographic axis is in AA dashed. This is the source of light S. It is producing unpolarized light, that means its vibrations in different directions. Ordinary unpolarized light from source is allowed to pass through the crystal. After passing through the crystal, the emergent light is found to be slightly colored and less intense. On rotating the crystal about the beam axis, color will not be changed. That means no change in color of the emergent beam. The resultant emergent light from the crystal contains vibrations only in one direction, is called linearly polarized light or linearly plane polarized light. Come to the picture. Another calcite crystal having crystallographic axis BB dashed parallel to AA dashed is placed along the path of the emergent beam. The emergent light from the crystal A passes through the crystal B, and the light is colored. In this position, crystal A and B are such to be in parallel position. Now, the second crystal BB dashed is slightly rotated. The intensity of the emergent beam from BB dashed reduces, and after rotations more than the initial one, the intensity becomes 0 of the emergent beam from the BB dashed. That means light is completely extinguished if BB dashed is 90 degree to AA dashed. On continuous rotation, that already I have told, the crystal B about the beam axis SO, the stage reaches the crystallographic axis AA dashed and BB dashed are perpendicular to each other, and the intensity becomes 0. That is, light extinguished. The crystal A is called polarizer and B is called analyzer. Now in this figure, unpolarized light from left side is falling on the crystal and its crystallographic axis, as already I have discussed. After the polarization, the vibrations is shown in the right side. Here ABCD, it contains the plane ABCD, it contains the vibration of plane. That means vibration of plane polarized light. ABCD is known as the plane of vibration. PQRS, it has no vibration. It is just perpendicular to the plane of vibration. This is known as the plane of polarization. The plane of polarization contains no vibration. Plane of vibration contains vibrations. Malus law. When a completely plane polarized light is incident on an analyzer, the intensity of emergent light varies as the square of the cosine of the angle between polarizer and analyzer. This is the unpolarized light is falling on the polarizer. This is the axis of the polarizer. This is the plane of linearly polarized light. Now after passing through the analyzer, this is the axis of the analyzer. So its angle is theta with the angle of the polarizer. So the Malus law states that the intensity becomes I is equal to I naught cos square theta, where I naught is the intensity of the incident radiation. Polarization by reflection. This phenomenon was discovered by Malus from the glass surface. He found that the polarized light is obtained when ordinary light is reflected by a plain sheet of glass. Here in our picture, incident ray is falling along this direction at an angle of I, and it is reflecting along this direction and coming to our eye, and this is refracting along this direction. So this light is polarized or partially polarized. I am discussing the conditions in later figures. This is the incident ray falling at an angle of theta. When unpolarized light is incident on the surface of a transparent medium, for example water, glass, etc., some part of light got reflected, this is reflected, and some part of light refracted through the material. At a particular angle of incidence, the reflected ray is completely plane polarized and vibrations are parallel to the surface of the glass slab. Particular angle is called Brewster's angle. Brewster's law. When an incident light is incident at polarizing angle theta p at the interface of a transparent medium, the refractive index of the medium with respect to the surrounding medium is equal to the tangent of the polarizing angle. If we represent n as the refractive index of the medium with respect to the surrounding medium, then Brewster's law represents n is equal to tan theta p. Theta p is the angle of polarization. Using Brewster's law, we can calculate the polarizing angle of a medium whose refractive index is known. For glass, the refractive index is 1.55. The polarizing angle in air, that will be calculated as 57 degree for glass. Double refraction. When unpolarized light is incident on an anisotropic crystal, for example calcite. Here we are using calcite crystal in the when unpolarized light is incident on an anisotropic crystal, here it is calcite crystal, there will be two emergent plane polarized light. The refracted ray that obeys the laws of refraction is ordinary ray. This is the ordinary ray, and that does not follow the laws of refraction is known as extraordinary ray or E ray. Here an ink dot is placed on a plane of paper. Now the calcite crystal is placed on the plane of paper. Now it is rotated. On rotation, there will be, on placing the calcite crystal, there will be two images. On rotation, one image of the ink dot is fixed, another one will rotate. The ink dot that is rotating is extraordinary ray, and that is fixed is the stationary ray. That is fixed is the ordinary ray. The stationary image is known as the ordinary ray or O ray, which is produced by the refracted ray and obeys the laws of diffraction. The rotating image, this is the rotating image, is known as extraordinary ray or E ray, which is produced by the refracted rays and does not follow the laws of refraction. Inside the double refraction crystal, the ordinary ray travels with the same velocity in all directions, and extraordinary ray travels with different velocities in different directions. Inside the crystal, there is a particular direction in which both the rays travel with same velocities. This direction is called optic axis. This is, suppose, calcite crystal. It is placed on this text. Now there are two images. On rotating, its intensity is decreasing or increasing. It becomes prominent. Now when the thicker edge is placed, then the image becomes more clearer and intense. Thinner edge, its intensity decreases. The refractive index is same for ordinary ray and extraordinary ray, and there is no double reflection along the optic axis. Along the optic axis, the refractive index of E ray and O ray is same, and there will be no double reflection. That means there is no separation between the E ray and O ray. They will travel along the same direction. Polarization by scattering. Just as unpolarized light can be converted to partially polarized light by reflection, it can be polarized by scattering also. This is known as Rayleigh scattering. This is the picture of the Rayleigh scattering. Rays are coming from the sky. The spherical scattering of rays in the blue part of the spectrum. This is why, this is the cause behind the blue color of the sky and other vibrations is coming to Earth. Now let us discuss in broader way. Since light waves are unpolarized light, this is the unpolarized light wave, is falling on the molecules, then atom is composed of large number of atmosphere is composed of large number of molecules. So light waves are electromagnetic in nature. It will vibrate the electrons of air molecules. Perpendicular to the direction in which they are traveling, the electrons then produce radiations that are polarized perpendicular to the direction of propagation, and in other directions these are partially polarized. However, there is no polarization parallel to original direction of incident ray. Light perpendicular to original ray is completely polarized. This is completely polarized, perpendicular to the direction of the original ray. This is the direction. This is partially polarized or unpolarized. This is also unpolarized. Circularly polarized light. When two electric field vectors are at right angles to each other with same amplitudes, remember same amplitude, superpose each other, the resultant light will be circularly polarized. Here in our figure there are two electric field vectors of same amplitude. This is one, this is another one. So at this point this is the electric field vector E, and perpendicular to this, this is the electric field vector along this direction. Now its resultant is along this direction. Now for this one, the electric field is along this, that means this is the electric field, this is this electric field vector, the electric field component is along this, so its direction is along this. So here this is the diagonally vibration, so this is a linearly polarized light. Now come to this picture. On shifting one wave by 90 degree, here the purple wave is shifted by 90 degree. This is our eye. Our eye receives the light, rotates. How? This is here. Now this point, this is the intensity along the electric field along the same direction. Electric field along the same direction. Here E is 0. Now E is for the purple one, E is increasing and so on. So again its electric field vector, the resultant for this point, the resultant electric field along this direction. Similarly with this motion, what will happen? The resultant electric field will be in circular loop like this along this direction. That means our eye receives this light, rotates, swing around this circular pattern. Here it is anti-clockwise. The light is circularly polarized. Elliptically polarized light. When two electric field vectors are at right angles to each other with unequal amplitude, superposed each other, the resulting light wave will be elliptically polarized. Back to the previous one. Here the electric field vectors at different planes having different amplitude. Suppose this is the y-axis. Electric field vectors has its amplitude is Ey and its x-axis electric field vector, its amplitude is Ex, and from this figure it is evident that Ex is not equal to Ui. So when they are superimposing, they will produce elliptically polarized light. Come to this animation. So they are superimposing and they are producing beam of elliptically polarized light. This is the front view. This is the direction of propagation. This is the front view of the polarized light, elliptically polarized light. Now, this is linearly, circularly and elliptically polarized light in a single animation. So here this is circularly polarized light. This is the elliptically polarized. This is the blue envelope is elliptical and the blue envelope is circular. This is the linear one. Now retardation plate. Retardation means slowing down. The optical device that makes a finite path difference between E ray and O ray by retarding the motion of one of these rays is known as retardation plate. Commonly there are two retardation plates. One is quarter wave plate represented by QWP. It produces a path difference lambda by 4 and phase difference pi by 2 between extraordinary ray and ordinary ray. Thickness of the quarter wave plate is T is equal to lambda by 4 into difference of refractive indexes of ordinary and extraordinary ray. Another one is half wave plate. It produces a path difference between the ordinary and extraordinary ray as lambda by 2 and phase difference of pi. Its thickness can be calculated as T is equal to lambda by 2 mu O difference of mu O and mu E. Why this is a difference? Basically, for negative crystals or positive crystals, mu A and mu E, depending upon negative crystal or positive crystal, sometimes mu A is greater, sometimes mu E is greater. That's why we have taken the difference. Optical activity. Certain substances like quartz, aqueous solution of sugar, etc. rotate the plane of vibration of a plane polarized light that passes through them. Two types of optically active substances. One is dextrorotatory or right-handed rotation. These substances rotate the plane of vibration of incident polarized light in clockwise direction, that is towards the right of the direction of propagation of light. Its example is quartz. Another one is levorotatory or left-handed rotatory substance. These substances rotate the plane of vibration of incident polarized light in anti-clockwise direction, that is towards the left of the direction of propagation of light. Aqueous solution is the example of aqueous solution of sugar is the example of levorotatory substance. How it works? So this is the unpolarized light. It is falling on the filter. So this unpolarized light, actually this is polarizer. It's correct. It's polarizer. So it is coming from this one. It becomes linearly polarized. Now this light is passing through the polarimeter tube. What happens? Say here some liquid is placed or some particles or some material is placed which has huge number of atoms here. Now this will change the direction of the plane of vibration. Now after emerging out from this polarimeter tube, so these are the vibration that we are getting. So analyzer will analyze its vibration. So On rotation of the analyzer, suppose from the initial axis of the analyzer, it is changed to alpha in clockwise direction. This is alpha plus. We are getting the light. This is known as dextrorotatory substance. If for this substance, if the analyzer has to rotate counterclockwise, so then this is the rotation on the axis of the analyzer. Then this is alpha minus. This is this type of rotation. When the analyzer has to rotate the counterclockwise, this type of material is known as or substance is known as a levorotatory optically active substance.